Okay, so I have a short little presentation and then we'll dive in to the ctmm package. But I wanted to motivate the kind of purpose and agenda for this package, which is a package for statistical analysis of animal tracking data. So putting GPS or other types of tracking tags or collars on animals and seeing where they go in time. So I'm just going to give a little introduction and I'm going to focus on one problem that's fairly well solved now statistically, um, which is estimating and not underestimating the space use of tracked animals. And I'm going to talk a little bit about the solution, and then some of the more statistical underpinnings of the methods involved in the solution. And it involves dealing with the non-independence of tracking data, the fact that these are time series data. When you track an animal's locations in time, you have a time series data. And then we'll get into the actual package and how you use the package. Okay, so let me introduce what these data can look like. This is tracking data on wood turtle in the Shenandoah Valley in Virginia. And these circles are error circles that can be fairly large. So you expect 95% of the time the circle encapsulates the true location of the wood turtle. And I colored them by time so you can get a sense of how the turtle is moving around as it's being tracked. And in this case, the turtle's movement is not that much greater than the actual location error on the GPS device. And also you get a lot of missingness in the data here because wood turtles like to go under things. And when they go under things, you don't necessarily get any GPS signal. So these data can be complicated in many different ways. Irregular sampling schedule, large location errors, and then the other one that we'll focus a lot on is the amount of autocorrelation in these data because they are time series data. So the kind of overall goals we have in analyzing these data and how we want to do our statistics in this package is that one, we want to account for the temporal autocorrelation in these time series data. And we do that with stochastic process models. We also want to account for sampling irregularity. Some people have nice regularly sampled tracking data. A lot of people do not. And also you might do one study 1 year with one kind of device and do another study years later with a much better device at a much better sampling rate. And so you might have not only irregularity in the individual sampling, you might have mismatch between studies or devices. And the way we account for that is that we use models that are defined in continuous time. So the animal has a location at all times, not just the times where you sample the animal's location. And we're going to account for location error if we need to with a location error model, one that we're careful about how we specify those parameters, where we get that data. And we're not going to assume a particular model. So there's a fair number of methods available for animal tracking data, and pretty much all of them are based on like one specific movement model that the developer of this method put together, and it probably worked really well for their data set. So we're actually going to do model selection and test some of the assumptions and see how well the models are doing. And another important thing that is kind of, this is more specific to movement ecology, that people estimate lots of parameters and then they just provide point estimates. And I think part of that's because it's so difficult to get good confidence intervals when you know the data are not independent. But we're gonna give uncertainty estimates for all of our parameters that we estimate. The big example of this would be an animal's home range. How big is an animal's home range? That estimate it's been almost ubiquitous in the literature that people only provide point estimates because their methods that they use only provide point estimates. And then if we want to go to population level analyses, we're going to propagate the individual uncertainties into the population estimates as well. That's been the other side of the coin for working with point estimates, is that the uncertainties weren't propagated up into the population level, which impacts those estimates as well. And we do that with hierarchical models. And in the methods I'm going to talk about, we work as much as possible to reduce the bias and error by using the best methods available or the best methods that we can derive from first principles with different techniques that I won't be able to get in too much, but are in the published papers associated with the methods. So the first thing I want to talk about, which is the primary concern of animal tracking data, is the temporal autocorrelation. So everyone here is probably has a much more intuitive grasp of spatial autocorrelation, which is different but related. So for spatial autocorrelation, the key phrase is that everything is related to everything else, but near things are more related than distant things. And it's really easy to get examples of that, like this elevation map of the US. This elevation is very spatially autocorrelated. Elevations nearby tend to be more similar than elevations far away. And if you were to imagine a spatial process with the same mean and the same variance that was not spatially autocorrelated, it would look pretty crazy. It would look like this kind of noisy elevation with no correlation, no relatedness from one point to the next. It would be physically implausible. And autocorrelation is very informative. A lot of times in many processes, the actual autocorrelation has most of the things that we're interested. It's not always the trend of a process that is the only interesting thing. A lot of times the variance is also interesting, and a lot of times the correlation in the variance is interesting as well. So for a time series, the statement would be that for something like a movement process, the location of an animal closer in time, locations of an animal that are closer together in time are closer together spatially than on average than the locations that are further apart in time. And the way we quantify that is with the autocorrelation function, where we look at the correlation at all points that are a certain number of time lags apart, where the time lags are in terms of how we sample the data. So if we sample the data, we track an animal's locations every hour, then at 1 hour apart, we would expect for a larger animal that locations 1 hour apart would be very correlated with each other. Whereas something very small, like a little mouse, that might be almost not correlated at all because they can move around their home range very, very fast. Like a little mouse will get around in an order of a minute, whereas a large, like an elephant, an hour is like nothing. It takes them weeks to get around their range. And the sampling frequency can influence and does influence our ability to detect autocorrelation. So the actual movement process itself will have a certain amount of autocorrelation, and we will or we won't detect some or all of that depending on how we sample the process. So if we coarsen the data down, as in this example, then we see at one time lag out, we see much less autocorrelation than if we had the finer sampled data. And if we keep coarsening the data, we see less and less autocorrelation. In this case, it becomes totally insignificant if the data are sufficiently coarse. Yeah. So the actual way we are going to visualize the autocorrelation is not with the typical ACF function, because the ACF function is really for putting these significant spans, and doing a test for autocorrelation, which is something you would normally do for looking at the residuals of a fitted model and seeing that if the residuals meet the assumptions of the model, which is that they're independently sampled. Uh, so we're actually looking at the movement process, and we know it's autocorrelated. So we don't, I mean, a significance for test for that is still useful if we've resolved it, but 99% of the time you have, because you don't have to track animals with that much resolution to so that they do have autocorrelation. So we want to visualize the autocorrelation, and we want to estimate the autocorrelation in an unbiased way. So the better method to do that is actually the method of variograms from spatial statistics rather than the ACF function. So it's basically the same thing, but it's upside down, and it starts at 0 if you don't have any location error. We'll get more into this, but the way it works is that instead of plotting correlation versus time lag, we're going to plot how far apart the locations are on average, or how the square of how far apart locations are uh, with a certain time lag apart on average. But the x-axis is the same. We're still looking at time lags of different lengths, and we're averaging over this square distance on the y-axis rather than calculating a pairwise correlation on the y-axis. So for animals that, for locations that are sampled very close together in time, the animal doesn't have time to get very far. So the semivariance will have a very low value. And if you don't wait any time at all, and there's no location error, then the animal won't get anywhere because it can't, it's got to move at a finite speed. And if we wait a long time, the animal will get some distance away on average. But if the animal lives within a home range, you can wait as long as you want, and they'll only get so far away. And then you get this asymptote that we'll get more into. And another important thing, in addition to the asymptote, is the scale over which you get this asymptote. It corresponds to the same way that the ACF function decays to 0, as the autocorrelation is no longer seen as you coarsen the data, for example. So this kind of asymptoting time lag scale is the time scale over which autocorrelation decays. But that's for an animal that you observe to be moving around in its home range. In some cases, you track an animal and it might be migrating or dispersing or having some sort of range shift process, and you never see it moving around in a well-defined home range. It kind of wanders around for the entire observation period. And so in that case, the semivariance function will just the semivariance will just increase and increase. The longer you wait, the farther away the animal will get on average. In the time series literature, they would call this they would call this a kind of non-stationarity, but that word gets used for very different meanings. So I'll just refer to this as an animal that's not range resonant. And there are other ways to visualize autocorrelation too. If you talk about repeated movements, such as like a canid species that patrols around its territory every day, like sniffing around, you might see periodicities. So there's a way to estimate the spectral density function, which is just looking at the ACF function in the frequency domain to draw out these periodicities. And then also, if you have changes in these periodicities over time, then the way that people look at this kind of information is with spectrograms. So these are tools that you would see people use in many other places in ecology other than movement ecology. You would see these, for instance, in looking at bird songs or like electric eel, electric signals and things. Okay, so the largest impact of autocorrelation and not dealing with autocorrelation is that when you look at your confidence intervals and your standard errors, if you don't account for the autocorrelation, then you assume that your standard errors and your confidence intervals are calculated from a bunch of independently sampled data. But that means that you believe this effective sample size is very large. It's the nominal sample size of the data. And so you overestimate, you have this large denominator here in the standard error essentially, and then you're making your standard error way too small because the amount of information, the amount of independent information you have in your data is not that much. And so your better calculated standard errors would be much larger than if you ignore the autocorrelation. And I'm saying this statement's kind of specific to movement ecology where you would only see positive autocorrelations, which is there are other kinds of autocorrelations that you would never see in like spatial or movement ecology where you're talking about a continuous process. Okay. So if you ignore the autocorrelation, then your standard errors, your confidence interval widths are underestimated. But there are cases when you're not doing like a linear regression or something that's linear like that, where the autocorrelation also has an impact on the point estimate itself and not just the uncertainty. So you can get incorrect conclusions because of the bias or because of thinking that your estimate is much better than it actually is. Okay, so the main thing I'm going to go over, which is like a big part of the ctmm package, is space use and the problem of underestimating space use. There are a lot of other things in the package as well, but this is probably the big solved problem that a lot of people go to this package for. So this is an empirical example of a black bear on one of the Great Lakes. And this is some data in red, some tracking data of a black bear. And these two estimators, the contours you see, these are both supposed to be estimating the bear's 95% home range. So where is this bear going to be 95% of the time? And they're basically the same estimator, but the one on the left assumes that these are independently sampled locations, and the one on the right does not assume that. The one on the right, we fed a bunch of candidate autocorrelation models, and then we did AIC-based model selection, and we selected the best one. And then we did the same kind of distribution estimate, which is a kernel density estimate, but based on that selected stochastic process model, autocorrelation model, rather than an assumption of independence. But otherwise, the estimators, the kernel density estimators, are the same. And also included here are representations of the uncertainty of how big or how small this area might be with the dash contours that are more easy to see on the right panel, because the right panel assumes the data are non-independent, and so the effective sample size is very low, as it turns out for a black bear that moves really far over a long period of time. So there's quite a bit of uncertainty in how large this bear's home range is, whereas on the left, the estimate comes out to be fairly certain that the bear will be here 95% of the time. And the size, the uncertainty in the size, which is what we're representing, is not really, you can't even see that on the plot. And then that was just the first half of the data. So the second half of the data, which is in like an orange gold colored here, you can see it does not cross-validate well with the distribution estimate on the left that assumes independence, which you might have thought initially, well, that one looks better. That one fits the data better. It must be the better estimate. But it's not predictive going forward into the future. It does not cross-validate well at all. This is supposed to contain, if the bear is doing the same thing in the same range and it hasn't like dispersed or migrated or something, these contours are supposed to contain 95% of future bear locations that are, independently sampled. On the right, it's actually uh, it, it's a little too small, if anything. It has a little bit less than 95% of these future bear locations. So in this case, with distribution estimates like this, ignoring the non-independence, it doesn't just give you confidence intervals that are way too small. It also, the point estimate can be very underestimated. If you ignore the temporal autocorrelation and tracking data, you would come to the conclusion over and over that your animal's home ranges are smaller than they actually are. And how small it depends on how you sample and what the autocorrelation timescales are of the individuals you're tracking. So you might have some questions like, why exactly does this happen? How often does this happen in practice? Like, is this a general concern, or is this something we only have to worry about for black bears near the Great Lakes? And how does this problem get solved? So the why is not too hard to answer. So here I simulated data from a known process. I simulated the same amount of data from a known process where this simulated animal takes about a day to cross its range. And on the left, I simulated 100 points over the course of a year. So between every pair of points in time, the animals cross this range a couple times. So it's pretty much in a completely different place, and there's not very much autocorrelation. And this kernel density estimate here on the left is assuming there's no autocorrelation, and it's not that bad. It's pretty good. This is about what the animal's home range, the true home range is, which I know because this is simulated. But then on the right, we simulated 100 data points, but only over the course of an hour. And this simulated animal takes a day to cross its range. So in an hour, it doesn't really get anywhere. And there is actually a density estimate, a home range estimate on the right as well, but you can't even see it behind the plotting symbols. It's so small. And like if you don't know any statistics at all, you would know just based on biological intuition that this estimate on the right is wrong. Like you didn't collect good data, you put it into this method that assumed independence, and you just know it's wrong. You know this animal is going to get farther than it actually does. And so this is the simplest explanation of why this happens. You're just not collecting enough data, and the data that you did collect is just way too autocorrelated. So it's all basically the same. So this is an extreme example. And then an actual tracked animal, how extreme will it be? It'll just depend on how extreme the sampling is. So does this happen in practice for empirical data? So first I want to say that the actual method we use here, kernel density estimation, is like the best known family of methods for estimating a distribution when you don't have any good sense of what the parametric model might be, or you don't have good covariates where you could even build a parametric model. But this is all for independently sampled data. So before the methods in ctmm, there were no kernel density estimation techniques for autocorrelated data. And so we introduced a variety of, there's a variety of methods here. They all work together. It's just basically methods on top of methods with different bias corrections and whatnot in the ctmm package. If you do the basic home range estimating, you're using probably about 4 or 5 different statistical methods all at once to get the best estimate out. And earlier on, when we were working on this, there were a lot of people that would look at these plots and say, well, the tighter one looks better, I don't really trust you guys. The math in your appendices is complicated. That's not very persuasive to me. So what we did was we got all the tracking data from all of our collaborators, and then we just said we just want the range resident individuals. Don't give us migratory individuals. Just give us range resident individuals. And then we're going to just do a huge cross validation on this. And we published this in Ecological monographs. And we did the same kind of analysis I showed you with that bear example, where we did a leave one out. I mean, not leave one out, excuse me. That's the worst thing you can do. We did a block cross validation where we leave half out, the first half, and then the second half. The first half is the training data set, and the second half is the cross validation training data set, the cross validation data set. Same as the bear example. And then what we found was that for empirical data, the conventional estimates were on average 2 to 20 times too small, depending on what method you were using. So the better methods, and what the one I showed you is one of the better methods. On average, it's only like 2 times too small for an average across empirical data sets at this time. But there were methods that were much worse that were on average, they were 20 times too small. And because this is dependent on the autocorrelation, which is dependent on the sampling rate, as our tracking devices are getting better technologically, this bias was getting and is getting worse. So the better the data makes using the bad, the older statistical methods worse over time. So this is we just some just to show you examples of what these cross-validation curves look like as we on the x-axis here is how many home range crossings you observe in the animal. And if you observe a lot for most of these methods, a lot being maybe hundreds or thousands of home range crossings, then you get good predictions from the older methods. But if you don't, then you get an answer that is not predictive. It's too small. And it's very sensitive to the method you're using. Some of these are, like I said, on average 20 times too small empirically, and some of these are on average only like 2 times too small, which is still pretty bad. And then so we did this empirically, and then we also did simulations from known truth, and we did these simulations based on the models that we selected on the empirical data. So they're kind of empirically motivated simulations. And then we could show that the area estimates are underestimated by the older methods, until you get effective sample sizes into the hundreds or thousands. Whereas the methods we put together, and this is the best that we had at the time, it was good to around 4 home range crossings is what you need to have an answer that wasn't too biased. And we can get now with the newer methods, you can get down to about 2 or 3 home range crossings and get a reasonably small bias. Now the variance and the uncertainty will be huge, but at least you will know it's huge. Whereas with all these other methods, you only get a point estimate. And there's some references for that. And let me just, it's 12:38. So I'll just wrap this part up and we'll get right into the code. So how did we fix this? We use continuous time stochastic process models to model the autocorrelation, and then we base everything we calculate, whether it's a home range, whether it's how far the animals are moving, how fast they're diffusing. We base these all on these stochastic process models. So let me show you, because I don't want to run out of time. Let me show you the different autocorrelation models that we're going to be fitting today and what they look like. So we go. This is not, oops. I'm sorry. I pulled up the wrong sort. There we go. There we go. Sorry, I pulled up the wrong video. Okay, so this is on the left here is a real African buffalo sampled hourly. And on the right here is the best fit process if you assume the buffalo is moving in such a way that you have independently sampled data. And all these older home range methods and a lot of techniques that are still being used, like regular resource selection functions, they all assume this kind of model on the right. But if you really had data that meet that assumption and you animated them in time, then this is what they would look like. It would just be jumping around in an uncorrelated fashion. So the next most common model that gets used, for instance, in Brownian bridges, this is what it looks like. So on the left is the same real buffalo. And then on the right, this is a Brownian motion process, the best Brownian motion process that's, most like this actual buffalo data. And the two things that you can see there is, one, it's pretty jittery compared to the buffalo's real motion. And also it doesn't have a home range. It just diffuses forever. So it's gone now, and it's going to get very far away if you wait long enough. And then after that, you get to models that were much less commonly used. This is the Ornstein-Uhlenbeck process. So this is a process that's basically Brownian motion in a home range. So it's very jittery like Brownian motion. You can't, with both this process and Brownian motion, you can't estimate how fast the animal's going or how much distance the animal travels because this process can't resolve that. It's a fractal motion process. But if you have coarsely sampled data that really looks that jittery, then this would be appropriate. And then next is the integrated Ornstein-Uhlenbeck process. Oops. Which is also an Ornstein-Uhlenbeck process for the velocity rather than location. And this actually, you can see persistence of motion here now. So this model was first started being used by people doing animal tracking by Devin Johnson for marine data with the crawl package, because they wanted to estimate speeds with Argos data, which has much larger location errors than GPS data. And because they're working with marine data. And so they use this model to do that. And this is the model behind the crawl package, if you've ever heard of the crawl package. But this model doesn't have a home range. So this animal will keep diffusing or dispersing endlessly forever as well. And then the last model we'll talk about in our model selection is a model which combines the features of the Ornstein-Uhlenbeck process and the integrated Ornstein-Uhlenbeck process, which is a model that has persistence of motion. So you can use this model to estimate speeds and distance traveled, but it also has a home range. So this process will stay around in the home range. And we call this at the time that we developed this model for looking at Mongolian gazelles, and we called it the Ornstein-Uhlenbeck foraging process. Although that's probably not the best name because it applies to things that don't necessarily forage. And okay. So now I'm going to get into the R package here. So this is all I'm using scripts that are on GitHub that anyone can find. They're in the ctmm learn GitHub repository. So we keep and maintain our workshop scripts, and you can see when they've been updated. And so we have workshop scripts for a number of different topics. I'm just going to go over two today, which is like the introductory script on fitting the autocorrelation models, and then AKD, the autocorrelated kernel density estimation script for home range estimation. But there's a bunch of other topics as well. So this is the ctmm intro script. This will just get you into the basic autocorrelation models that I talked about. There are help files for this package on more things that are in the workshop scripts. So like fully documented functions, and there's always newer functions being developed. There are vignettes for like long form documentation for like 5 different topics that are a little maybe easier to read than the workshop scripts. And if you're interested in, okay, and there's frequently asked questions. There is a Google group. If you have questions, looks like I have some questions to answer from this week. I try to get on that. I've been getting a little, when I got this position, it slowed me down a little bit, but now I'm speeding back up. So feel free to jump on there. There's a GitHub issue reporting. There's a Dropbox of all the manuscripts. So you'll see in the help files what methods are being used, and we keep a Dropbox of all the different manuscripts for the methods that, so if you want to look into like how it works, or maybe what the different options might mean, or things to consider, the validity. We're pretty open about where we think like a method that we develop will not work very well on. We don't hide those kind of things, so that should be explained in the manuscript. And then more recent than the CRAN version right now is pretty up to date, but the development branch on GitHub is usually even more up to date. And then you can always see what's new. And I don't have the right package installed to run that, looks like. And also, if you have friends that don't know how to use R, there are move apps on for all all the core package functions. There are move apps on the MoveBank move apps platform, and new ones coming all the time. So the first thing I'm going to do is just load the package, and I'm going to talk for 1 minute about importing data. So you coerce your data into the right format for everything to work in ctmm, which makes some assumptions about projections and the data structure, specifically location errors. And those things have to be in the right structure for you to proceed with some of the analyses. So we have to kind of get you through this funnel first. And this will work 100% of the time if you get MoveBank formatted data. If you don't, the easiest thing to do is to replicate the MoveBank format, which is there's a link there to what those conventions are. And if you don't follow that format, it's probably still going to work, because the code for this is like pages and pages of code for identifying different location columns and getting that in there. But here is an example of a zip file that has a MoveBank formatted CSV, and you would just, they updated my computer here, and what is this? What is this? Data is not a recognized. What? Oh my God. don't even know what that means. All right, this is embarrassing. Well, hopefully the other stuff will work. Um, okay, that's weird. I apologize for that. They're constantly, I'm at work. I don't have like admin permissions on this computer in my office. They're constantly updating things, and one of these updates broke something. I hope most of this works. It worked at home. It used to work here. I didn't just, uh not test anything. I Okay. Okay, so I was able to load this example data set that I'm actually going to be working with rather than that file just fine. It has a help file associated. This is some African buffalo data from Kruger, from Paul Cross. Uh, this is now in the environment now. You can see that it's a list object, and it has 6 elements. And the first, if you look at any one of these elements, they're ctmm telemetry objects. And the basic structure is that there's longitude and latitude and time in there. And they're named by the names that were given to the different collars or animals. And then there's some summary information that we can get on them as well. The first thing you want to do if you're thinking about, you always just want to plot the data. So we have some plotting options here. Here's just plotting the 6 buffalo. You could color them differently. Here I'm coloring them according to the rainbow. And here I'm using a special function that will color them so that also by the rainbow, but so that buffaloes that are closer together spatially have more distinct colors. So this is a special function that you can put in like different color functions and get this to come out. So this is very useful. You're plotting a whole bunch of individuals on a map, and you want them to come out distinct from each other. That was surprisingly non-trivial to make an algorithm that'll do that, believe it or not. It's like comparable to like the traveling salesman problem, and it's not exactly solvable. But there's a lot of other options, things you can color by, including the sun and the moon and the seasons. One thing that I'll say, when you import your data, your data are automatically projected, and the default projection might not be the one you like. It's the one that's very safe. It's a 2-point equidistant projection, so you could have a big long migration, and then distances from the 2 foci which are determined by geometric median clustering, which is robust to outliers. Those distances would still be accurate. So this is a very safe projection. I got a hand raise.
I'll work with Mel.
Oh, you'll do that?
Yep.
Okay.
Yep.
Okay. So, but this projection, although it's very safe, this is where north is pointing on this projection. So it's not necessarily up. A lot of people want one with this is in the fact, but I keep getting asked this question, even though it's in the fact now and I cover it in all my workshops. If you want an azimuthal equidistant projection, you can just use this geometric median command that's built into the package. And now we have an azimuthal equidistant projection, and this will have north equals up if we plot that. Right. And projections are really important for getting accurate calculations. So you want a locally flat projection like this. So the center of this projection is right here at 0, 0, and it doesn't go very far. So the distortion here is very low. So either of these 2 projections would give you very good results with this study. All right, so these again, these buffalo, there's 6 of them. They have names. I'm going to pull out one just to talk about fitting the autocorrelation models. This is Scylla. This is what she looks like if you plot these points in time from red to blue. That's a good way of just seeing is if it's all red on one side and all blue on the other, then that's like a range shift. And so that you would think differently about these data. Here we're going to do home range analysis today, so those would not be necessarily good data for that. And then now we're going to calculate this semivariance function. So this is, I calculate this semivariance function. So on the x-axis is time lag. So this, I'm considering pairs of points that are this far apart, say a half a month apart. And then on the y-axis, it's if I wait half a month, on average, how far does the animal get squared? That's the y-axis. So if I don't wait long, the animal doesn't get anywhere. And if I wait a long time, the animal gets pretty far. But if I wait a really long time, it doesn't make that much of a difference because this animal lives in a home range. It's only going to get so far away, right? It's not going to leave its home range. Not this animal, not one we sampled the data. There's some options here I won't go over. If you don't have too much data, there's an option for more accurate confidence intervals that I will not cover. And even though this is a very fast Fourier transform method, it just can't handle like millions of data points. So next, the function we're going to go over is the ctmm guess function. So we're doing nonlinear fitting. So that means we have to use optimization. So we want like a good starting guess. And there is a function that will automate these starting guesses. That's the ctmm guess function. And you don't have to do it manually like this, but the first time you do it, that can be useful. So we have the variogram, empirical variogram of the data in black, and then we have a theoretical variogram here in red. And then we have a few different parameters here with starting guesses. And we have our variance. That's the effect it has is where is that asymptote? That's the variance of the home range. We have this position autocorrelation timescale. That's how long this autocorrelation in position lasts. And then we have, if we can see it in the data, if the data are finally sampled, we have this velocity autocorrelation timescale. And if it's not there, you just see a straight line initially. But if it's there, you have this initial curvature. And this is something you only have in finely sampled data. And that means you have data that you can actually estimate speeds and distances. So conventionally, people just do straight line distance, but that's not always meaningful because animals don't move in straight lines between 2 points unless you sample them very finely without location error. You can play around with that to learn, but in general, once you get your head wrapped around everything, you would run it non-interactively like this. And almost all the time, these automated guesses would be good. And then we're going to run ctmm select. And that's going to select a bunch of that's going to fit a bunch of candidate models and then select among them based on some sort of information criteria. And then this is the slowest part of the analysis, but it is computationally O of n. So if you have 10 times more data, it will only take 10 times longer. So if it seems like it's taking a long time, you can always trim down to a little bit of data. And then you can say, okay, this is a tenth of my data. It'll take 10 times longer than this. How long will it take to run everything? And then also this is you have multiple individuals tracked. So that's embarrassingly parallelizable in that you can, if you have 12 cores on your computer, you could easily do 11 of these at a time. It doesn't take a ton of RAM. I'm going to stop this. Oops. There we go. And I'm just going to load. I've already got this run. And oh no, no, what does this mean? You tell him, oh my, this is that same error. Oh my God. Oh no, 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 this is my fault. This is my fault. This is my fault. I'm not in, I'm not in the right working directory. So I'm for someone that develops an R package, I am very bad with computers. Thank God. Okay. All right. So this is the different candidate models that it attempted. You see OU is the Ornstein-Uhlenbeck process. It has a home range, but it doesn't have any persistence of motion. OU big F was the one that had both of those properties. And then anisotropic means that it fit an elongated distribution. And then OU little f, this is when you can't distinguish between the time scales, the position and the velocity autocorrelation time scales, which you probably will never see that selected unless you have a shorter track of like a central place forager that's kind of zipping around its entire home range. In that case, those two time scales are very close together. And then it never got to the independently sampled model because these are nested models. And so I'm just going to throw those in there. You see how fast those fit, right? Those are like super fast because there's not really doing anything. And then now if we do AIC based model selection, you can see that going from the selected model that has all this autocorrelation in there to the IID model, AIC goes up by 38,000. All right, so very much selected in terms of AIC. The selected model, excuse me, the IID model, if we run summary on that, we just get this Gaussian area estimate with very narrow confidence intervals and very large degrees of freedom or effective sample size. We can plot the Gaussian distribution associated with our autocorrelation model, which is here like nothing. This is the IID model. We can plot, oops. Here's what that looks like, very narrow confidence intervals. We can also plot with the semivariance function. So this, again, black was empirical. Red is now the theoretical of this model. And if this were IID data, you would just jump straight up from 0 to whatever the variance is with this amount of expected noise. So all this white here in between is where the confidence intervals don't overlap. So this means you have a really bad model for a long range of time lags. And then you can also look at the residuals if you want. With the residual function, you can plot them. The assumption here that these residuals are supposed to meet is that they are supposed to be independently sampled bivariate Gaussian. And so that Gaussian's plotted there, and you see all this structure in there. And you can also plot their ACF with the parallelogram function. And you can see that over basically half a month, you have a whole lot of autocorrelation in the residuals. That's because we didn't account for any of the autocorrelation, and the process is tons of autocorrelation. And it takes about half a month for all that to decay away, which is about, that's pretty much the location autocorrelation timescale that we're thinking about here. So the selected model, when you look at that, you have all these extra parameters from the autocorrelation. So you have this position and velocity autocorrelation timescale. You have what's here, a Gaussian root mean square speed, root mean square velocity or speed estimate, and you have a diffusion estimate. And then you have a whole bunch of different degrees of freedom or effective sample sizes, not only for the mean and the area, but also for the diffusion and the speed. And the area effective sample size is very low now. It's like 18. And that's because that's about how many crossings you actually observed in the buffalo, because it takes a couple of weeks for it to get across its range. So the effective sample size really should be about 18. Yeah, so I'll skip. I'm going to skip a little bit of this, and we'll go down to, I'll plot. This is the selected model, which is the OUF model, but anisotropic. Just to emphasize what that means is that it's an elongated distribution, whereas the isotropic OUF model, which is not, it was not much worse, but it is a symmetric distribution that's the same in all directions like this. Okay. And the varigrams, the match is much better, although this is real data, so it's not perfect. You can see that there's some, it takes some time for the animal to cross its home range, it takes some time for this curve to asymptote. And if we zoom in, it's picking up some of this initial curvature for the speed. And then there is some, discrepancy here. It's not perfect, but it's not terrible. We can look at the residuals. I mean, this is real data. It probably has a much more complicated true model than anything with just 4 parameters. We can look and plot the residuals. Again, they should be bivariate normal. This takes a second to plot because it's got to make that little null distribution. Looks much more normal and unstructured than the previous, and we can look at the autocorrelation and the residuals, and there shouldn't be any. And for most time lags, there's the expected amount of significance, 5%. What you expect with random chance. There is a little bit, a few time lags in the beginning where there might be a little unmodeled autocorrelation, but it's like 6%, not like 100%. And it's just a few lags. It's not like months of, half a month of lags. So the improvement in the model is tremendous. All right, I'm going to get to the next part now, skip a few more things, and we're going to talk about the home range estimation now that we can select a good model. So the basic function for that is AKDE, autocorrelated kernel density estimation. And I'll point out 2 arguments that we won't cover. One is that you have boundaries that you have a shapefile for, like fencing or a river or something that the animal won't cross. You can include that at the kernel level with these SP arguments. And the other thing, if you have like strong covariate dependence, like bathymetry for animal in the water, or elevation or something for an animal on land, and you do a resource selection model in the package, you can include that back at the kernel level for your home range estimates. So you can have these dependencies in there as well. And that can be important because kernels, the statistical efficiency slows down quite a bit when you have boundaries and strong selection preferences for kernel density estimation. Okay. So I'm going to load that buffalo data again, reproject it so north equals up. This time I'm going to pull out Pepper because she's problematic. So Pepper, here's what she looks like, the data. Here is, I'm plotting sorted by size, the sampling intervals. And so she was scheduled to be one hour. But it actually, her collar switched over to 2 hours for a reason that no one knows, and then has all these big gaps in the data. And then there's these smaller sampling intervals too that there's no explanation for. So there's a lot of collar malfunction on Pepper, which is why we're using her in this example. You would do the model selection before kernel density estimation. Here's the selected model. It's an OUF anisotropic. It has this velocity and location uh, in there. I'm going to also fit an IID model, and that has a much larger effective sample size. And then we're going to just do a regular KDE, and then we're going to do an autocorrelated KDE, and then we're going to do an autocorrelated KDE where we weight each point optimally to account for the fact that the sampling uh, changes on this individual. This is something you generally don't need to do unless you did something weird like change your sampling. Like some people like increase their sampling rate in like calving season or something like that. So in that case, you would want to do this. And now we're going to plot um, the optimal weights just so you can see what they look like real fast. I'm still calculating one of those. Mm, we're almost done. I'm going to, there we go. Yeah, so there's the optimal weights. You get more weight where the locations are sampled less. So where there's those big gaps, you get more weight. And you get more weight on the 2 hour data than the 1 hour data. So initially it was mostly 1 hour, but with a lot of irregularity. So the weights are lower. And then when it jumped up to 2 hours, the weight jumps up because those data points become more valuable, more informative. I'm going to set an overall extent so I can compare the plots. And then here is the regular KDE. You can see it's very tight to the data, very little uncertainty. There are uncertainty bands there. Um, here, 1,000, 1,700 degrees of freedom, narrow confidence intervals. Then here is the KDE, AKDE. It's larger. The point estimate is larger, and the uncertainty is a lot greater. And then here, in this case, the weighted AKDE will be a little different. So this point here, this part here in the kind of middle, if you can see my cursor, this part was oversampled initially at 1 hour sampling before the sampling went down to 2 hours. So in the unweighted, you get too much emphasis there. In the weighted, this is like a better kind of spatial representation of what the actual distribution is. But it generally doesn't change the size that much. The size estimates are pretty similar in terms of their uncertainties. Um, and then here, some further code down here if you're interested in population level mean estimates, population mean area, or population range. If you have multiple individuals tracked in a population, there's some more code down there. But I believe I'm supposed to stop about now for questions.
Okay, let's see. You have a couple questions on poll, and let's go from the first one. So, is there a standard formula for what the sampling rate should be with respect to how fast the animal moves or move much distance it travels? That's the first question.
So there's not a formula that I know of, but there is a package called Move Design, which lets you do a kind of like a power analysis or something for setting up the experimental design, where if you kind of have some impression, maybe there's some other people who track this species, maybe you can pull a similar species from MoveBank, and you can kind of figure out how you need to set your sampling rate to estimate the things that you're interested in. So that's called Move Design, and there's actually, I think, hmm, I thought, all right, we'll put a script in there for the Move Design, but it's pretty easy to use. It's point and click.
Okay, next question is about the GPS coordinates. So does the data that get input into the code have to use GPS coordinates? And also there's a follow-up question. For instance, can this package be used to plot or model movement in captivity where the GPS is too large at scale?
Um, so uh, GPS is the most common. You can also do Argos tracking. You can do VHF triangulated data. Although right now it won't calculate the error ellipses for that. You have to use a different package for that. You can do UHF or VHF trilateralized data. It can do any kind of tracking data where you have a point estimate for where the animal is, and you can also supply an error circle or an error ellipse. The kind of tracking data that this package is not appropriate for would be like array data where you get a ping when you're near a receiver. Like in hydrophone arrays for fish, although there are some hydrophone arrays where you can get a trilateralized, a multilateralized location estimate, and those would work. But the ones where you just get a detection, like that, or like a MODIS type detection for a MODIS array, um, uh, or camera trap data where you have an individual that you can identify and you know he was at this camera and this camera and this camera. That's a very different observation model that requires, I mean, I want to implement that at some point because that's a common type of data, but those data are not presently appropriate for the package. And then now I've forgotten the second part of the question. Data, animals that are in like zoo animals or something, or agro stuff. Um, you can do it. You definitely want like if there's like fencing, you want a shapefile for that, for like the density estimates and thing and the and that sort of thing. People have used the package for that. I haven't seen any huge problems with it.
Okay, thank you, Chris. So the second question is, can I estimate home range if the variogram does not reach the asymptote? Sorry, asymptote.
Yeah.
Yeah, go ahead.
Yeah. So I would say generally no. Although I'll caveat that. If you have a bunch of individuals and some of them have ranges and some of them just it goes up and up forever. A lot of times that's because those individuals just they were dispersing or something. They weren't resonant. You can, in some cases though, it might be that most of your individuals you got a lot of data on, and then some individuals you just had a short period of data. In which case, yeah, you could estimate from that. You're going to have a very uncertain estimate. It's probably not going to be very useful to extrapolate from that. But most of the time, if it's not like it's because it's a really short period of data. It's probably because the data is not range resonant. In some cases, you can kind of classify your individuals and that these are range resonant and these are my home range area sizes. And then these other ones, these were not range resonant. They were nomadic or migratory or something. And then what you can do is you can estimate their ranges. They're going to have huge uncertainties. They're probably going to have a lot more bias. But you can say these are like the nomadic ranges or the dispersal ranges or whatever behavior that corresponds to. So there are cases where it's still useful to pin those numbers down as much as you can and include them. You just don't want to lump them together and say like, you want to separate those behaviors.
Okay. Chris, and the next question is about fitting multiple individuals. So is the parameter estimates among individuals are fully independent, or is there a way in CTTM to fit hierarchical models that partially pull some parameters among individuals?
Yeah. So the models are fit independently, and then the hierarchical model that's actually there's some of that at the end of the script I was going over. That it works like a meta-analysis where you take the individual fits and then do a meta-analysis model to get the population level models. So at present, um, you don't get any borrowing of information on a poorly sampled individual from the population. But that you can still do that. And the reason I use the meta-analysis framework is because computationally it would be too slow in most situations to fit a hierarchical model to all individual tracking data at once, because these are time series models, and even with the fastest methods, they're kind of slower, a lot slower to fit than like a GLM or something. But in principle, we could implement like a posterior prediction for the individual level models, drawing that information from the population level estimate. Uh, I'm not sure how useful that would be, so we haven't done that at least presently, but maybe we'll do that at some point. If someone has a need for something, I'm more motivated to solve it. Um,
Okay, thank you. And the next question is, so would it be possible to remove the autocorrelation by subsampling randomly data at a rate equal to the limit of autocorrelation shown with semi-variogram?
you can coarsen the data down. So like for these buffalo, it takes them about 2 weeks across their range. And you can coarsen down. Actually, there's a ctmm script on let's see, what is it called? It's a ctmm learn script. It's called not ctmm, and it's actually telling you, it shows you how, like at what how much you should coarse into to meet different assumptions, like for independent locations or for independent steps. That doesn't require as much coarsening, but usually it requires coarsening as well. Yeah, you want to sample down to a certain interval size. What you don't want to do, and I don't know if you were implying this, but I have seen people do this, is just like randomly drawing like 1% of the locations or something, just a random 1%, because those could have any sort of time lag in between them. And so some of those will be very auto correlated together, and some of those will be less auto correlated. You want to like thin down to a certain interval is what you want to do, like regularly sample data as much as you can at that interval. And there are ways to estimate autocorrelation in this package to know how much to thin it. And there are tools in both the move package and the AMT package that will resample the data for you.
Okay, thank you, Chris. The next question is about, uh, is there a best model option of vignette for estimating nesting location rather than entire home range?
Nesting location. I mean, it's probably going to be the mode of the home range area. And there is, did I export? Let's see. I don't know if I exported and documented that function. It is in the package internally. Oh, no, I don't think I did. It's in the package internally. If you can't find it, just get on the forum and ask me or email me, and I'll give that to you. I think pulling out the mode of the density estimate, because that's where the animal is most frequently, I think that would have to correspond to the nest.
Okay, thank you. And then finally, a general question. So if we are collecting location data through triangulation instead of GPS color,
Hmm.
how should we minimize location error and improve the accuracy of estimates in spatial temporal modeling context? This is for
Uh,
like fast-moving small mammals.
yeah, I would. So first, I would say quantify your errors, and there are methods to do that. Like there's a method of uh, length, I think, and I think there used to be in our package that would calculate an error ellipse for a triangulated location based on that method. Um, Last I remember, you have to like install the old version of R to run that package. I think there's some commercial software that does it too. I actually have a postdoc that I'll probably have him implement that because he's going to be working on VHF stuff. Um, I but you can quantify those errors, and then there's a whole vignette and a whole workshop script and a whole paper on including the location error model in your movement modeling. I didn't do that in this workshop for time, but that's important for a lot of people, especially with triangulated locations. But for actually minimizing the errors of a triangulated location, I'm not an expert on that. But there's a lot of literature on it. I'm sure people know much better than me about, actually, on the ground best practices for that.
Thank you, Chris. I just refreshed the page, and there's some additional small questions that are specifically for the package. So first one, are the functions in the package able to take environmental factors into account when estimating home range?
Yes. So there's an integrated resource selection function method in the package for estimating resource selection. And after you've done that, and there's a workshop script on this that can walk you through this. After you've done that, you can then go back and estimate your autocorrelated kernel density estimates with that resource selection imposed at the kernel level. So that if your individual has preferences to some resource, then you'll see that reflected better in the home range estimate. And generally, this has if the selection is strong, it can have a strong effect on the kind of spatial distribution of the probability mass of where the animal is going to be, but it usually doesn't. I mean, we haven't explored this in depth, but it usually doesn't have a huge impact on the size of the home range unless there's a lot of spillover, like for like a fish onto land or something, because the fish likes to be near the shoreline. In that case, all this spillover is bad, and that would be one way to fix it.
Okay. Thank you. Since you mentioned about fish, there's one question about marine animals. So do you have an example of using the barrier file for the model? Does that look at like polygon files or raster of the whole area? So the person who asked question have a marine animals moving around small islands.
Yeah, I don't think I have an example in here, but it's really simple. You just have a spatial polygon object and you stick that in as an argument, and then it just works. And I know people have used this, and we just got a paper accepted, I think in Methods in Ecology and Evolution on this technique of imposing the boundaries at the kernel level rather than at the distribution level.
Okay.
So
Thank
Jack
you.
Collins is the lead author on that.
Oh, okay. Okay.
So I think that's on the bioarchive now, but I don't think it's on the website yet.
Okay. We can always check the papers later. Okay. One last question. So are there plans to have this package be able to handle MODIS or receiver type data?
Yes. Long term, I absolutely want to do that. So the kind of data I said was not appropriate, which is like MODIS, like hydrophone arrays, like camera trap. I know how to do it. I want to do it. I just gotta apply for some funding and sit down and spend my summers doing it. It's much more complicated. The observation model is very nonlinear, and you have information. Not only is the animal near a receiver, you also have information when you think the animal's not near a receiver. So it's a very different information. It's very complicated. Nothing like GPS, where you assume the error is just giving you something a little bit off from the truth.
Okay. Thank you so much, Chris. I think that's all the questions from the audience.